Thank you everyone for attending this seminar on a Friday evening. The title is Mathematical Modeling in Professional Sports. My name is Abdullah Zafar, and my colleague who we're lucky to have on the call with us today is Farzad Yousefian. And so we both come from Sport Performance Analytics Inc. And this is the first in our seminar presentations as part of the series run by UTSPAN. Really the end goal, or like the overarching goal of this presentation, is to really break down what it means when we say we're measuring performance, right? That's really kind of the job of the data analyst and the performance analyst, right? You're trying to quantify performance in order to drive performance, really, right? And so on the left here, we have, for example, like the actual performance, as in this case, it's soccer, football, which will be the majority of actually all of the examples we give today. And on the right-hand side, we have the actual data, or the quote-unquote quantification or measuring of that performance, right? But like the one thing that kind of stands out when we look at this is there's almost like this disconnect, or there's it's almost disjoint, where the performance looks one way and then the data looks another way, right? And so again, the goal of modeling and again measuring performance is to minimize that disconnect, right? You want what you're measuring and what we're quantifying to reflect that original performance as naturally and as authentically as possible, right? And so the first way we can maybe shift that mindset is to, instead of thinking about data, right, we think of data as capta, right? And so what I mean to say by that is, when we say data, inherently there's this assumption, right? It's kind of passive, where we're given these numbers, and given these quantitative metrics, and those are the actual performance, right? Whereas capta is more of an active mindset, right? You have the performance, you have real life, and you're trying to capture that performance in some way through these numbers, right? And so it's a subtle difference, but there is there is a difference there in terms of passively accepting data versus actively trying to capture a performance through data. And so when we say capturing, right, again, we saw there's this kind of disconnect between the performance and the metrics, and that's because there are actually hidden layers that maybe we don't always think about in between, right? So there's the performance, then of course, maybe the first step is the actual engineering or the hardware involved in capturing that performance, or the digitization, we might call it. And so that would be like the hardware used. Is it GPS? Is it computer vision? Is it someone on their tablet notating these actions, right? Then there's the resolution, how frequently are the actions captured, the modality, again, automated, semi-automated, or otherwise. Then there's the actual game model. Once we've digitized our performance, there's the game model, and there's an overlap between the game model and metrics, right? But at the same time, they are two distinct steps. Where the game model, I'm referring to how do we understand the game, right? How are we going to even begin to quantify? Because our metrics are going to come from our model, right? And so the example I give here is is our model, or is our understanding of the game, is it discrete or is it continuous? So with this little figure on top, for example, we've taken the field and we've cut it into these discrete segments. So for example, this zone belongs to this player, right? If they're in this zone, then they're in this player, right? And so it's these very kind of clear-cut boundaries, or discrete dissection of the game. Or, by contrast, is it continuous, right? Are these zones blended in, right, as opposed to a stark boundary placed? Is it time independent or time dependent, right? So what's the temporal aspect here? Are we considering the match as a whole? Are we considering something more dynamic? What's the resolution of that temporal behavior? Is it, again, halves, quarters, 5-minute intervals, 1-minute intervals, second by second, right? Is it regular, right? Is it something where it is second by second, or is it maybe play by play, where of course the plays don't have the same amount of time? So those kinds of questions come into actual game model, right? And that comes between your digitization of the data and the actual analysis and metric output you get. And so we can see how the game model directly impacts what kind of metrics or analysis you pull out, right? If we consider something that was time, and if we looked at the match as a whole, our metrics might look different than if we looked at something that was time evolving. And so, again, for the purposes of today's presentation, we're going to be focusing mainly on these last two components here and how the model and metrics kind of play with each other. But in the back of our head, whenever we're doing any kind of analysis, we should be aware of all these steps involved, from the performance all the way to our output. And so the case study, or the kind of example we'll use today in terms of demonstrating that process of modeling something, we're going to try and model team movement. And when I say model, like we'll get into that into a second, exactly what I'm saying when I say model. But in general, right, team movement it's a very complicated topic, right? Because again, contrasting the left and the right, we have individual movement, right? So just the movement of one player, be it on a soccer field, or even you could imagine like tennis, or where there are like a single player sport. You're only concerned with the position and velocity of the single individual, right, and how they're moving. But once you now have group movement or team movement involved, first of all the individuals in the team are going to have unique positions. They're typically not going to share the same velocity. They're not going to be moving in some kind of matrix-like fashion where they're all moving in the same direction at the same speed. And not only that, they're not independent of each other. All these players are coupled with each other, as well as they're coupled with something else, like it could be the ball or the opposition, right? And so the complexity of our system has gone way higher, and it's not so easy to just use things like position and velocity to independently model these individual members of our team, right? And so again, this is the kind of problem or task we're going to be trying to evaluate today, or trying to step through in terms of how would we go about modeling this team movement. And so modeling, what is it in the first place, right? And so when we say model, right, maybe another like synonym for that we can use is representation, right? How do we want to represent something is how we want to model it. And again, this forms the platform, the basis for everything we do from this point onwards in terms of analysis, right? If we represent the team, for example, as a single point, well, then that gives us certain options and also restricts us with certain options in terms of what we can now analyze about the team, right? So these four kind of methods are all kinds of models or representations of teams that exist in the literature. And so just going one by one, we have a single point. So we represent the team. I mean, this is kind of just collapsing the whole team into one point. And then we can analyze the position velocity of that single point. Usually we call it the centroid, or the center of mass of the team. And we can see how that center of mass moves and changes over time in order to tell us something very broad and general about the team's behavior. Are they spending more time in a certain area of the pitch versus another, this kind of thing. And paired in with that, we have other kind of metrics like the width of the team or the area covered by the team, right? But these are all, again, kind of collapsing the entire 11 players which constitute a team and their independent behaviors into one kind of one-dimensional entity, right? And so this is what we call homogenization of data. Again, it has its upsides in that it's very simple to implement and very easy to get some quick general results about the team. But the downside is, of course, homogenization. We're losing a lot of the intricacy and complexity in our team behavior by doing this. Then we have things called Voronoi diagrams or Delaunay triangulations. And so this is like breaking down this kind of single team entity into triangles, right? So now instead of saying, okay, there's one shape or one point that represents the whole team, it's this set of triangles. So we've triangulated the team, and then we can see, for example, like what zones each player occupies based on triangulation, what kind of passing options based on who is connected in this triangle are available to each player, right? And so again, this is still a discrete model, discrete game model, because we are setting these very sharp boundaries. It's a step up, right? We don't homogenize our data as much as a centroid, but at the same time, it is a discrete model, which we, might also see as a drawback, since movement in real life, it's not really chopped up in these like sharp boundaries this way, right? And so that's where the next kind of model comes in. This is what's called a pitch control model, presented at Barcelona in 2018. And so they introduced this concept of, again, creating these player zones, but now using bivariate normal distribution, right? So instead of having these sharp boundaries for our players and what zones they occupy, it's more of like this continuous Gaussian that models that based on the player velocity and their position. And so the different colors would represent, okay, like what's the likelihood of a player to reach a ball if it was in these different colored areas. And so this is a way of, again, creating these player zones, but instead of a discrete fashion, doing it in this continuous fashion, right? Which might resemble more of real life. Now, the final model, right, is this notion of using flow fields to represent team movement, team motion. And this is actually the model that we're going to really pick apart in this kind of presentation. And this is actually a model that Farzad and myself came up with and presented last year in Athens. And so it's a more dynamics-based approach, right? So again, these last two are both continuous models, but this one is based more on distributions, and you could say maybe a more statistical approach to, again, modeling team movements, whereas the flow field approach is maybe rooted more in like a physical, dynamical approach to modeling team movements. And so the main difference between these two is mainly by using this dynamics approach, we can actually integrate all the player motions in order to extrapolate information. Whereas even with the pitch control model, each player's motion is still not completely integrated, it's just summed up, right? In order to create this distribution. And so whatever model you choose, right, it's just be aware of, yes, how are we representing this team, and what are the limitations, drawbacks, as well as what are the actual benefits, right, based on the application needed. And so the other thing to keep in mind when we're building a model is what is actually a good model. Like, how do we know, like, I can't just represent team movement as anything, right? Like, how do I know, for example, if I'm going to say, okay, we're going to use a flow field to represent team movement, why? Like, why is that a good way to think about team movement, right? And so a good model, a way to kind of maybe like test if you have a reasonable approach to modeling something, you should be able to balance three things. Number one is the intuition behind the model, right? And this is a bit more subjective, right? Modeling is not it's not all objective, right? There are subjective choices whenever you're modeling anything. So the intuition is, does your representation or model align with domain experience, right? And so this is where it's not necessary, but it's useful to consult with coaches or players or people who are the actual actors or people who are directly involved in the performance, to consult them and see, okay, is how I'm understanding or how I'm modeling your performance actually in line with how you are viewing your own performance, right? And so intuition is a huge thing. And then the metrics, you can actually objectively test the metrics that come out of your model. This is more in the results phase, where, okay, first of all, like, can they be logically derived? Are you just like adding 2 and 2 and then calling it, oh, this is our player evaluation model? Or like, you should be able to logically step through why, when you call a certain metric, is it actually measuring what you're measuring, right? You should be able to show that logically. And the second part is also important, is, are your metrics stable? Are they reliable, right? If I run the model once and I run it on another scenario that's quite close, are we going to get like similar results? That's usually a test for stability. And then bring the last point, the last kind of pillar of good models, right, brings these two subjective and objective aspects together in terms of results. Do they make sense? That's the subjective aspect of it. and how do they compare to established results. And so, of course, just because your results from your model don't always line up with established results, that doesn't mean it's not a good model, right? As long as you can still explain it. But these are ways to test your model and see, okay, is the model reasonable or is it not? So let's use these criteria. Really, the last two are based on results. And so we'll use this first criteria of intuition to see, okay, does our team movement as flow model, could this be a good model, right? And so let's actually compare and contrast flow and football, right? And so they're both temporal aspects. They're both continuous and time independent, right? It's not necessary that like you can have time independent flows that aren't like they don't follow a specific rule, as well as football, right? It's also time independent. You can have chaotic actions happen at whatever point in the match. And the spatial aspect of it, these are also they align in their intuition, right? Again, they're smooth or continuous, we could call it again, right? Which lines up with how we view real life. People don't randomly, like abruptly change direction. Movement is always smooth. And it covers the space, right? So our flow field, what I mean by that is our flow field covers the entire field, which is the same notion that we have in football, right? The players and their actions aren't limited to where they are, but of course they're open to the entire field of play, right? And then in terms of actual structure of the team, again, there's these similar kind of notions that exist in football and exist in fluid dynamics or flows that suggest that this team movement as flow is a good model. So for example, in flows, you have stability, turbulence, chaos, all kinds of things we can also see in football, right? Like, is the team structure stable? Is it turbulent? Like, is it chaotic? Is it all over the place? What are the transitions between stable and unstable moments? There are things called boundaries and flows and like this coherent structure, which again, this would be like the notion of stability in football teams. And then this notion of force and pressure in terms of flows, which can be translated in the football intuition of the tempo the team is playing at and the integrity of the team structure. And so again, these kinds of parallels, this is again, a subjective, but since there are all these parallels, it gives us a suggestion that yes, maybe team movement can be modeled as flow. That would be a reasonable approach to take. And so how do we even do this, right? Because this is where we are generating a flow field, right? And so the basic concept here, the big concept is using what we call radial basis functions. This is a mesh-free method of interpolation. So the goal, right, or the task is we have these positions of the 11 players on our field, all moving in different directions. They're not evenly spaced out, right? So how are we actually going to turn these 11 data points, or in this case, outfield players, so 10 data points, into a flow field that covers the entire space? Right? And so that's why we call this a mesh-free method of interpolation, because the players are not sitting on a nice grid, right? They're not sitting on a mesh. And so this notion of radial basis functions allows us to create this flow field, a dense vector field, regardless of how our players are spaced out and regardless of what velocities they have. Right? And so we're not getting into too many technical details here, but please, afterwards, if we have questions about this, feel free to ask. But the notion here is we're going to, this is our radial basis function. It has to be continuous. That's our one thing, because again, we know movement is continuous. It doesn't have abrupt discontinuities or abrupt changes. It's always smooth. Then we're going to take our 10 players, right? We're going to perform this kind of weighted sum over all the players based on which direction they're moving in. We have to solve for their player weight. So that's the unknown, which we'll solve for. And then we're going to use some kind of, we call it a radial basis function kernel that is smooth and consistent. So this is the interpolant, we call it. And so again, the keywords here are Your kernel has to be smooth and consistent. One example of these would be a Gaussian, right? A Gaussian would be both of these things. So smooth, we've already talked about. It's continuous, right? There's no sharp edges in this. And consistent means that if I looked at the flow field at the point of the actual players, the flow at that point matches up. So the flow field and the original player velocities are consistent with each other, right? And that's important because you don't want to lose the original information when you're creating your flow field, right? And so in this way, you're actually interpolating and extrapolating information without losing the original information.
Okay. Yeah, Abdullah, we just have a quick question here. If you go back to 2 slides back.
2 slides back.
This one, yeah. What do you mean by integrity of team structure? Like what is the definition of integrity here?
Right. So this will make a little bit more sense when we go into a couple slides from now when we talk about divergence. But if we want to look at this kind of figure down on the left, bottom left here, what I'm talking about integrity of team structure is, are there 2 different behaviors of the team occurring? So like, is the team moving in one coherent unit? Or is, like, for example, one half of the team moving in one direction, has one intention, and the other half of the team is splitting off and doing something else? So we see in this, for example, in this notion here, they all come this way, and then half the team kind of peels off in this kind of route, the other half goes the other way. There's a split occurring, right? And so that's what I mean by integrity. There's almost a breakdown in the integrity of team structure in the middle there, if that kind of initially answers the question. So,
yeah, I think that was good. Ethan was the one that asked that. Are you good with that answer? Does that make sense? Yeah, he says yes. So let's continue on then. Thank you.
Yeah, great question. Thanks. And so, again, we've now created this flow field. What do we do with this? So one of the ways we might evaluate or start to build our analysis using this flow field, because the flow field is our model. Now we're working towards the analysis and building metrics out of our model. And so what we look at is something called the divergence in the flow field, right? And so this is the rate of change in player density over the field. So we can view this as a kind of heat map where you have the flow, and the flow is telling you something about the team. It's telling you about the team's intentions, right? They're leaving this area of the pitch and they're entering, some of the team is entering this area of the pitch here, and some of the team is entering this area of the pitch here, right? And so we can see that in the flow field, but when we map it to divergence, right, we create this heat map, it becomes even more obvious, where the light areas over here represent areas of divergence, or areas where the team is moving away from, and the dark blue areas are areas of convergence, or areas where the team or the players are moving towards. And so even actually just going very quickly to Ethan's question again of what is team integrity? Well, we see a breakdown in integrity over here again, right? Because we have these 2 separate areas of convergence happening, where again, half the team is going one way, the other team, half the team is going in another direction, as opposed to a single synchronized action of the team. And so we have this heat map visualization. In addition to this, sometimes, it might build a bit more intuition, is to visualize this divergence in 3 dimensions as a wave, right? So this is almost literally, now we're thinking of the team flowing back and forth over the field. And so the peaks of this wave are areas of divergence where they're moving away from, and then they tend to converge in the valleys of this wave. And so from a physics kind of perspective, right, if we were to take this interpretation, this divergence wave, it's a map of the player potential, right? If you think about a ball sitting on top of a hill, the ball moves from areas of high potential to areas of low potential. It rolls down the hill, just like these players are rolling down the peaks of the wave into the valleys. And so players tend from these high potentials to low potentials. And this, again, if we're talking about logical derivations of metrics, which was a condition for a good model that we highlighted earlier, this gradient on a potential is actually physically what we would call a force, right? So, of course, in real life, we have physical forces like gravity, magnetism, all these kinds of things. These are all the gradient or the slope of this kind of potential. Now, of course, I'm like, this force, quote unquote, that we're modeling here is not a physical force. It's not like this actual gravity, it's nothing like this. It's more of that's why we call it a pseudo force, right? It's more of a representation of a force, and we call it the driving force. So what we mean by that is how intense is this team moving as a unit from a peak into a valley, right? How forceful is their movement in terms of their convergence into a single point? And so if you have more players converging into a single point with much higher intensity, right? Not only is your integrity higher, but we would say the team tempo is being played, the tempo of the match or the tempo of the team is being played at a higher rate, right? Whereas if you have, let's say, a relatively calm wave where the intensity of these peaks aren't so high, right? There isn't this great discrepancy between peaks and valleys. Well, then the tempo of the match is a bit lower, right? It's more stable, it's more calm. And so that's why, like using this notion of a pseudo force, we can now derive a metric for team tempo based on this intensity or this force of movement, as we might call it. And so it turns out tempo is actually has quite a few tactical and physiological implications, right? It's a term that's actually widely used in the actual footballing space, right? You say, Barcelona is playing at a high tempo, or they're not playing at a high enough tempo to break down the opposition. So tempo itself as a word, as a concept, as an intuitive idea, it's grounded in the sport. Now, the goal of this model was to actually quantify that. And now we have a number to associate with tempo as opposed to just a conceptual idea that coaches might talk about. And so, again, the tactical and physiological implications here actually we took data from the Canadian women's team at FISU 2017. And so because they had GPS and heart rate monitors on them at the time, we were able to match their tempo, the metric we derived from the wave, with their actual physiological data. So things like their heart rate, their average speeds, their work rate, total distance, all these kinds of physiological things that the strength and conditioning coach for the team or performance analyst of the team would find valuable in terms of evaluating performance, we're able to actually correlate them with this tempo metric. So that's, of course, important in terms of the physical preparation of players. But the additional layer that tempo gives us is that we actually get a representation, a tactical representation of the team's strategy in terms of this divergence map, right? This kind of heat map of the divergence, which tells us what areas of the pitch, this is kind of like an aggregation over the entire match, right? Showing us, okay, this team tend to converge in these areas of the field and tend to diverge away from these areas of the pitch. And so it gives us a kind of value or a kind of target area for different players. And so that maps out the team's strategy in terms of where are they really trying to attack from or defend from, if we were thinking about from the opposition standpoint. But thinking again to the physiological correlations, right? We can now look at, okay, the players that are playing down this wing of the pitch will need a certain physical preparation that players in the middle may not need, right? Or forwards may not need a specific physical preparation based on this correlation that maybe this winger or a certain defender may not need, right? And so it really helps break down or customize the physiological or physical preparation plan for each of the players based on their tactical role by integrating the two. And just as a quick comparison, the kind of standard map that's used in football and a lot of sports is the heat map, right? And so just to compare and contrast the divergence map versus the heat map is just telling us, okay, what is the time spent by players in a certain area of the pitch, right? But it's not really saying, there's a lot of information lost here. It's not really saying, okay, maybe the player, because maybe the ball never got to this area of the pitch, maybe the play broke down, right? And so it's not really helping us tell us about the movement intention of the players. It's more of like this kind of one-dimensional thing of, okay, this is time spent in a certain area of the pitch, whereas the divergence map helps us extrapolate a bit more tactical information, right? And that gives us a bit more customizability and definition in terms of our player roles, both tactically and physically. Now, another avenue we went in terms of looking at tempo, right, is in the Danish Superliga. So this is the kind of first division professional men's league in Denmark. And so we used our program iScout GPS, which like implements this kind of tempo analysis. We ran it over 3 seasons, so 1,165 performances, and looked at 1,630 goals scored over those 3 seasons. And we found some actual interesting results from this tempo, right? First of all, in terms of the actual match results, all teams pretty much start off with a similar tempo, right? Again, as expected, everyone's kind of fresh at the start of the match. And so everyone has this kind of starting tempo, but as the match progresses, we're looking at 15-minute intervals here. The winning teams in green maintain a high tempo. The losing teams always seem to drop off, and the teams that draw are somewhere in the middle. So again, thinking about how we evaluate models and looking at results, do they make sense? Yes, this is kind of what you would expect, that the winners are able to maintain some kind of intensity and tempo, and the losers would do the opposite, and the ones who draw or tie are in between. And then looking at goal scoring moments. So we're looking at 1 minute before a goal is scored, 1 minute during the goal is scored, a minute after the goal is scored, and the average like 1 minute tempo for the entire match. We see that the goal scoring moments are significantly higher than everything else, again, expected. And not only that, there's a significant difference between the team that's scoring and the team that's conceding. Again, expected. You expect that the team that's scoring has done something significantly. They've played with a bit more intensity, which has allowed them to deconstruct the opposition and actually score that goal. So again, just using these results to be like, okay, does our model make sense? Do our metrics make sense, right? And of course, these line up with intuition. And the final way we kind of do that is looking at actual league table results. And so again, since we looked at an entire season, we were able to take the teams with the highest tempo, and we saw that at the end of the season, they actually ended up in the top of the league table. The ones who had like an average tempo were in the middle of the table, and the ones who had the lowest tempos were at the bottom of the table, right? And so tempo has this kind of implication. It shows up in all these kinds of different intuitive aspects of the match in terms of goals scored or minutes played or even league results. And so because it manifests in all these different ways, it's reasonable to actually take this tempo metric a bit more seriously now, and this model of flow fields as a reasonable approach to think about team movement. But if we wanted to do a little bit more with tempo and see, okay, like how we know that this happens, we know what happens now around goals, right? But how do these differences in tempo manifest themselves, right? And this question is the second part of analysis that's really important, because it's not enough, right? The job of the analyst is not enough to just say, okay, this happens, right? It's also important to communicate now to coaches, or find a way to take your metric or take your model to a coach or to whoever is like the practitioner, and actually help them implement it in their practice. So if we were to just stop the story here with the league table and the match results, it's nice, it's great, but the coach can't just go to the team now and say, okay, guys, we've got to play at high tempo, right? It's not like there's something missing there in terms of actual the ability to implement your model or metric, right? And so we're gonna, just the last part of this presentation, we're gonna look at a few different ways of maybe augmenting our analysis so that we can actually get to that stage of creating something that's implementable in terms of team training. And so just like our modeling, right, your analysis depends on how you represent your data, right? So what we're going to be doing here is time series analysis. We have a time series of tempo over the minutes of the match. And so we're going to be analyzing that time series to try and pick out insights that could be actually implemented in training. And so how we represent the time series will affect what kind of analysis we can do. And so there's 3 main ways. There's a lot of ways to divide up time series, but we'll stick to these 3 for now. So there's a parametric approach to time series, and this basically examines time series as an iterative process, right? So you have time point 1, followed by time point 2, and you're saying, okay, this is where like auto regression or forecasting comes in, where you're trying to use previous time points to say something about future time points, right? So that's what we call parametric. And the reason it's called that is simply because you're assuming that your entire system or your entire time series can be represented by a few parameters. And so this is where like those would be the auto regression parameters. So things like moving averages or models like that. Then you have non-parametric time series, right? And so this is where you're actually looking at the time series as an entire entity by itself, and you're trying to pick apart different statistics about the systems, or what we call spectrums of the system, and we'll get into that in a second, what that means. But the point is, instead of looking at this iterative process, we're actually trying to say something about the system as a whole. And then finally, we have a topological approach to time series analysis. So this is a relatively newer field compared to the previous two, but by new, like, you know, I'm talking about still 1980s, 1990s, that's when it started to pick up steam. And so this is where we're actually going to, again, take a more dynamic approach to time series analysis. And we're going to say, okay, we have this dynamic system, and our time series is what we call a projection of that system. So again, just to wrap up this presentation, I'm just going to look at the non-parametric and the topological approaches to this analysis and apply it to our tempo time series. So we'll start with the non-parametric. And so the example we'll use here is something called a detrended fluctuation analysis. So it is kind of very similar to how it sounds, a fluctuation analysis. We're trying to say something about how this tempo series, how it fluctuates over time. Is it random? Is it correlated? Is it what we call anti-correlated? So correlated would mean if you have a low tempo value, is that followed by a low tempo value? Anti-correlated is more like something that oscillates wildly. So if I'm playing with low tempo, then do I play with high tempo, then low, then high, then low, then high, right? So is it random, correlated, or anti-correlated? And the way we do this is we take our signal, which again, it's non-parametric, so we're looking at it as this entire kind of signal as a whole, and we split it into these different segments. We detrend it, which means we fit some kind of polynomial and we remove the trend line. So in this case, we're using parabolas or second order polynomials. And then we look at the variance in each of these segments. So for example, the variance in this segment might be lower. The variance in these segments, when there's more spikes, might be higher. And we want to look at the average variance like in these different segments for different segments. So we look at segment size, right? The smaller, the finer I look at my tempo, how much fluctuation is there, right? And so typically it follows this exponential curve. And the exponent defining this curve is what we call the Hurst exponent, right? And so that's just kind of the mechanics of what the fluctuation analysis is. But the key kind of thing to take away from here is that we're trying to see, is our system, is our time series, is it random? Does it have that correlated effect, or is it anti-correlated? And the way we'll know that is via this exponent we call the Hurst exponent that we pull out of here. And so what that means, right? So this is, again, we have our fluctuation versus our segment size or scale, right? It's just, instead of putting on like an XY plot, we just put it on a log plot in order to get a straight line. And so there's a really interesting thing that happens here, right? What we're interested in is the slope of this line. So when the slope of this line is 0.5, this is what we call Brownian motion or complete random motion. That means the tempo of the team, the movement patterns of the team, they're completely random, unpredictable, right? But when you have a slope that's greater than 0.5, so between 0.5 and 1, right? This is where you have that correlated behavior, right? Where high is followed by high, low is followed by low. And so this is what we call fractal motion, fractional Brownian motion. There are self-similar patterns and structure that are being produced in the team motion, right? And so the point where the slope crosses over from this slope of 0.7 into that random 0.5 is what we call the crossover time, right? And so the crossover time, if we think about what this is saying, it's saying, okay, your team is moving. They're moving with some kind of structure, with some kind of purpose, with some kind of combined intent. How long are they able to maintain that structure and that pattern in their movement before it breaks down completely, right, into random motion? That's what we're trying to get at here. And so it turns out this crossover time occurs every 30 to 40 seconds. Essentially, how often is the team's pattern changing, right? And this is like actually a general result. It's not a specific team. Some teams, better teams, will be able to maintain their structure for 40 seconds. Weaker teams for like somewhere around 30 seconds, right? But in general, crossover time happens at 30 to 40 seconds. Why is this important? How is this augmented our analysis? How is this now a bit more implementable into training? Well, this, again, thinking about the physiological results and what kind of things go into the physical preparation, this 30 to 40 seconds now gives an outline for the coach to, okay, how long should my drills actually be planned for? How long can my team actually maintain some kind of pattern, right? So it goes again into designing drills for the coach and like thinking about opposition, right? How long does the opposition tend to hold a certain pattern before it breaks down, right? So again, just a little bit more insight that the coach can take and plan and scout opposition or prepare tactical plans or physical plans for their own team. Adding a layer of complexity to it. So we're going to get into multifractals, right? Just a really quick, Jamal, there's no questions at this point so far, or are there?
Oh, we did have one question that I thought you almost finished. I was going to see it to the end, but
okay. Sorry, if it is general, then I'll get through these last few slides and then we'll get to those questions then.
Sure.
Yeah. Right. Okay. So just multifractals, right? We talked about fractal motion or fractional Brownian motion, which was defined by that single Hurst exponent of about 0.7. Of course, real life is really complex. And so you can't just use one single exponent to define that complexity, right? And so real life, we deal with multifractals. So there's multiple Hurst exponents, that's how we can think of this, which define our system. And so all this is doing, right, is, again, it's a fluctuation analysis, but now it's a multifractal fluctuation analysis. And the idea is now we're just using a moving window and computing the Hurst exponents over our time series, over our window, like in each of these small windows. And then we're creating a probability distribution for a system, right? Or what we might call a spectrum of Hurst exponents. So this spectrum is essentially saying, okay, what is the probability that our team is going to have random motion, right? When the Hurst is at 0.5. What is the probability that our team is going to have structured motion, right, in this range between 0.5 and 1? What is the probability our team is going to have this kind of weird oscillating pattern of structured to unstructured, rapidly fluctuating back and forth between 0 and 0.5, right? So this gives us a bit more of a holistic picture of how our team or how the team is structuring the movement patterns. And so what's really interesting is how in the first 10 minutes, teams have this pattern which is biased towards the 0.5 to 1 range, right? And so essentially we say that this kind of distribution, it has a short left tail, right? Because it's biased toward the right-hand side of the distribution. And so that means not only is there persistent or actual structured pattern, as we'd expect when players are fresh in the first 10 minutes, but it's also insensitive to large fluctuations, right? So that means, in this case, that if, let's say, a team is dominating their possession, they have a very good structure in terms of their patterns. If there is a disturbance to that, let's say the opposite team has like a quick counterattack, even let's say goal, right? There's a disturbance or a perturbance to the team structure. When they're fresh, they're able to recover that much quicker, right? And so that's what it means. It's insensitive to those large perturbations. Whereas when we look in the last 10 minutes, this kind of distribution bias towards this like rapid oscillation between structured and unstructured, you have a higher chance of disruptive moments and like the insensitivity to small fluctuations. So essentially, it's much easier to break down teams in these last 10 minutes. There's much more chaotic back and forth that occurs. which again, this lines up with intuition, right? With how we'd expect and how we actually observe team play to occur. And so the goal is to minimize these two spectra, right? You don't want such a big disparity between what's happening at the end of the game with what's happening at the start. You want it more like this distribution in the starting 10 minutes. And so again, last few slides here. We're just going to look at a different approach to time series analysis. This is called topological time series analysis, where we're looking at a dynamic system, right? So dynamic system, just kind of like what it is. It's saying you have a space, right, that defines the state of your team. So the state of the team, like where are they on the pitch? What is their tempo? What are the velocities of players? That's the state of the team, right? And then you have an evolution map. So if they're at a certain position in the field, how do they evolve and go to the next position, right? So these two things define your dynamic system. And so like your system is actually an aggregation of all the dimensions involved, right? So for example, if we take weather, right? A weather is a dynamic system, right? And it's an aggregation of all the things that are involved with weather. So temperature, wind speed, precipitation, geography, right? These are all different dimensions to the weather system that's aggregated. But each of those things I just mentioned, temperature, wind speed, all, like those have their independent time series, right? So like, and they're all kind of chaotic, as we know, right? No one can really predict. They're not very reliable, right? And that's because they're projecting that very complex weather system into only one dimension. And so that's why it's so difficult to predict things like weather, because you're judging it, a complex multidimensional thing, off of just one dimension of that thing. And so this is the kind of view of topological time series analysis, where you have your system and your time series is just a projection of that system. So just an example here, again, we have our system, like this is a pendulum that swings back and forth. Our state space for the system is something like a circle, right? Where you have position versus velocity. If you plot these things, sometimes it's called a phase space. And so, you know, the position and velocity have this relationship. And these two things, when aggregated, define the system holistically. But if I was to look at position independently, I'd get a one time series. If I was to look at velocity independently, I get another time series, right? So going from the state space or system into the time series, we're projecting it onto this time axis. Now the question is, if we're given a time series, can we actually go the other way, right? Can we actually take a time series, reverse it, and actually get the state space, right? And the answer is surprisingly yes. Like projecting is easy because you're going from 3D to 1D. But the reverse is actually you're saying, okay, I'm going to go from 1D to 3D. And not only am I going to go from 1D to 3D, I don't even know if it's 3D. It could be 5D. It could be 10D, right? But I can actually do that just using a one-dimensional time series analysis. And the proof of this is something called Hawkins' theorem. Again, technicalities we won't really jump into right now, but if questions are welcome afterwards. So the process for this is essentially creating this kind of matrix built from our time series, doing a singular value decomposition to determine how many dimensions we need. So for example, the 3 non-zero eigenvalues from our decomposition like imply that we have 3 dimensions in our original system. And so when we actually reconstruct our time series in 3D, this is the original system. And this is our reconstruction of the state space, right? So just very important to note here, you can see there's a clear difference. Like we don't have a perfect one-to-one reconstruction of what our state space looks like, but we have something similar. There's some key aspects here that are similar. And that, for example, we have these 2 holes, right? Or we have this kind of figure 8 shape that's warped, right? And so, again, like what we call this a diffusion or a warping. Our reconstruction is not a perfect reconstruction. It's a warping of the state space, but it gives us important information about the original dynamics, right? So again, like we call these orbits, these holes, we can see that there's 2 different distinct patterns in our original state. It can't be a perfect reconstruction, because if you could do that, then you could predict anything, right? Like this is, again, why we can't predict weather from just temperature, right? Because we don't actually get the entire weather state space back. We get this warped version of weather. right? And so it's not an accurate representation. But what we care about is, again, these features like the holes that tell us the behavior of the system. So just applying this to our goal scoring moments and tempo, right? These are those reconstructed attractors in 2 dimensions. And so we see the team that concedes has this kind of circular orbit. So again, thinking about like the circular orbit, we saw it with the pendulum, right? Where it's just going back and forth. It's kind of very predictable, periodic motion, right? And so we can see why that actually can lead to the goal scoring moment, because the team's movement has become predictable. It has this periodic aspect to it, that the team that scores the goal, before the goal, we see this ramp up. We call this a point attractor because we see how the tempo spirals toward this high value. Then we have chaotic, this kind of chaotic figure 8 kind of pattern, right, where the team that's scoring has high tempo, then low tempo, but in this very seemingly unpredictable fashion, even though it is structured. And then after the goal, then they go back to the normal rhythm of the game of high and low, then high, then low. Whereas the team that conceded the goal during this whole time, they were just stuck in their periodic orbit, right? And so this gives us some insight into why did a certain team's structure break down, right? What happened? But even more interesting, more importantly, right, is that instead of just saying, okay, the tempo was higher during the goal scored moments, we're actually saying like this is an entire minute, the entire minute leading up to the goal scored. We see a ramp up in this tempo. We see this changing dynamic that the team that conceded is not responding to, right? A minute is a long time in sport. It doesn't matter what sport we're talking about, right? And so this actually gives us a way to almost identify threatening moments in a match and identify when is a team actually susceptible or vulnerable, right? And again, if we watch any kind of sport, we kind of know, right? We kind of get this sense intuitively there's some kind of threat, right? And this is just kind of putting it in numbers, putting it like quantifying it in terms of these, what we call state spaces and attractors, right? And so just maybe wrapping this all up, how did we do, right? We set out to model team as this flow field. And so let's evaluate how do we do based on those 3 pillars we discussed of what's a good model, right? There's the intuition aspect, which we already went over, right? There's all these similarities between flow fields and actual football in play that make the intuition line up. There's the metrics we pulled, right? Again, they were logically derived, right? Going from the physics intuition of forces and potentials into actual sporting intuitions of tempo and intensity. And they lined up. They were reliable. They were stable, as we showed across 3 seasons, in terms of showing results. And then in terms of the actual results as well, we were able to find results that matched our intuition and were actually impactful and actually matched previous results or established results in the field. Like, for example, the 30 to 40 second kind of rule that we discussed in crossover times. And so overall, right, the flow field seems to be a reasonable model, right? And so this is how we might go. This is how the process we might follow for taking a model, thinking about a model. How do we represent, in this case, team motion, all the way through to deriving metrics, analyzing, and building meaningful results that can be implemented in the team setting. And so just some further ideas. We could then, another important concept in terms of models is how do you expand it? You don't want to answer all the questions in one go. You want a model that you can actually expand and build more things out of. And so we could think about individual influence of the players. We can think about pattern indexing, right? Like, are there, can we actually maybe maybe cluster different movement patterns, right? And then we can also think about opposition influence. So in terms of the dynamics, how does the opposition actually affect the dynamics of the team, and has the team affected the dynamics of the opposition? So that really is, here are some references in case, just some more reading for people if they're interested. My own contact, Farzad's contact, if people want to reach out with questions afterwards.